As I mentioned in the previous video, some of the words for equality we'll see are is, of, and yields. So in part B, 7 decreased by twice a number yields 1. What I want to do is find the equals word, and then I'm going to separate it into the left side of the equal sign and the right side of the equal sign. So on the right side, I just have 1, so I know that something equals 1, and that something is 7 decreased by twice a number. 7 decreased by, if I listen to the way that sounds in English, the 7 is decreased by means I'm going to take something away from that 7. 7 is decreased by twice a number. So that would be the correct translation for that sentence. Let's go to the next page. The next page is a tip about some commas. When I have commas in my sentence, in my mathematical sentence, the same thing as if I have commas in my English sentence, they do make a difference. Do not break your bread or roll in your soup, or do not break your bread or roll in your soup mean two different things, depending on whether or not there's a comma there. So let's look at what this difference would mean in the algebra sense. The product of 6 and a number increased by 5, okay? Or the product of 6 and a number increased by 5. Okay, so when I have a comma, there's a break, the product of 6 and a number, and then I'm going to increase it by 5. If there is no comma, there's no break. So it's the product of 6 and a number increased by 5. So it's the product of 6 and this whole group, a number increased by 5. Okay, so we want to be able to hear that difference. The product of 6 and a number increased by 5 is the second one with no parentheses. But the first one, the product of 6 and a number increased by 5, does imply parentheses. Let's try to get that translated down here in part C and D. The product of a number and 13, okay, the product of a number and 13, so that's going to be x times 13, which normally I would write with the number first. So the product of a number and 13, that is x times 13, or 13x. There was a comma right there underneath my line, so that was a break. Then added to 3 times the number. Gives is another equals word, so equals 4. Now let's look at that same sentence right again without the comma. The product of a number and 13 added to 3 times the number. So it's the product of a number and 13 added to 3 times the number. So the product of a number and 13 added to 3 times the number. This order difference is very important in the way I would write this equation down. Gives 4. We're going to solve this equation differently based on whether or not it does have parentheses. So I need to make sure that I do know when it does have them and when it does not. Okay, the comma is a stop. It tells me to stop and finish this part, do the product, then add 3 times the number. But when there are no comma, the parentheses are implied in there. The product of x and 13 added to 3 times the number should be written with parentheses. Something to keep in mind when you have a couple of different operations going on. Maybe you want to refer back to this page for notes on that. Okay, objective 5, or last objective for this section, we want to evaluate formulas. A formula is an equation that has some meaning tied behind it. So I'm going to write an equation with meaning, with real-world meaning, that's what I should say. Real-world meaning. That's really 2 words, but that's okay. Meaning. Real-world meaning. So for example, an equation might be area equals, equal sign looks awful. Area equals length times width. This is a formula that has some meaning. A equals LW, or it might be E equals MC squared. It's a formula that has meaning. Okay. Any other formulas you might know of, something that has meaning? These formulas right here are pretty common ones, like you've seen E equals mc squared. It's one of Einstein's famous formulas. Or area equals length times width. You've seen these formulas before. You know that they have a meaning associated to them. Okay, so any equation that we write, like this one here, can be a formula if I know what the meaning of x and y is, or x and whatever letter I happen to have. Oops, I'm trying to scroll right there. There we go. So this right here in the example 6 is a formula because I do know the meaning of the letters T and N. This is talking about a variety of cricket that chirps faster as temperature rises. I can approximate the temperature by counting the number of chirps per minute using this formula. T is the temperature and N is the number of chirps. What is a reasonable estimate for the temperature if you count 95 chirps in a minute? So I'm going to use that formula. I don't know the temperature. I'm trying to find the temperature when I have 0.3 times 95, number of chirps, plus 40. Okay, so I'm going to pull my calculator up here on screen. And we'll just multiply 0.3 times 95 and add 40. So 68.5. And as always, if I'm ending a word problem like this, I want to make sure I put my units on it. That was degrees Fahrenheit. So if you count 95 cricket chirps in a minute, it's probably 68.5 degrees Fahrenheit. In part B, we want to say what would we conclude if we counted 1,000 chirps per minute. Okay, so what's the temperature if, again, we have 0.3 times this time 1,000 chirps per minute plus 40. So let me go back to my calculator. Clear. 0.3 times 1,000 plus the 40 would be 340. And again, that's in degrees Fahrenheit. What would I conclude if I counted 1,000 chirps per minute? Well, it would have to be 340 degrees Fahrenheit, which is impossible without everything catching on fire. Water boils at 212 degrees, so that's awfully hot. So that would be my conclusion, is that it's not possible for there to be 1,000 chirps per minute. Another possible conclusion could be that there are multiple crickets and you're counting all of their chirps instead of the chirp of a single cricket. Okay, and that is the end of the first section.